believe it's the Democratic majority.
Stats class so that you can figure out how properly measure goals to figure out what kind of activity it is.
I like that.
Yeah, but you wouldn't know the material if you don't do the homework. Because they're not independent. There's a strong positive correlation between doing homework and doing well in the class.
If only someone had told me that my first math class.
Okay, so actually, okay, so are you ready to start? Has it been 10 minutes?
In 3 minutes, it'll be 10 minutes.
We're all here, right?
Let's begin. Okay, so the next thing is quadratic surfaces. Sort of comes from elliptical curves back in calc2, but probably don't want to mention that. It's not nice to say something without an intro of some sort. I'll just say it. Just going back to the days of conic sections where you're doing that's the general equation. Of course, in most of the things you've done, these guys were always 0. Right? And based on the values of the coefficients A, B, C, or any of these guys, you could actually turn things from an ellipse to a circle, to blah, blah, blah. Okay, so that's the general formula. We will use traces to help again. In general, all variables will be present. Okay, so in the idea of, in the case of cylinders, one of the variables was always missing. We just knew that was the axis we stretched the shape along, right? But here, all 3 variables will be present. So how do you draw that? Well, the idea is to sort of ignore one at a time, and then you draw what shapes develop from the other 2 variables, and then you sort of put all these traces together to make a 3-dimensional surface. Right? So that's sort of the idea. So if all 3 variables are present, we're going to break it down to 2, and then do it piece by piece, and then put it back together. That's the idea. Example, sketch. So I'm just going to put a little tweak to the last example we did and actually throw in just a z-square in there. This is called an ellipsoid. It's going to be the first one. And I have 3 more examples, but let's... Let's actually take care of that one first. It'll probably take up a lot of board space. I don't know. Okay, so the idea here is to use traces, and a good place to start with the traces is to start at the coordinate planes, right? So we're going to look at what does it look like in the xy plane, what does it look like in the xz plane, what does it look like in the yz plane, and then we sort of put all these shapes together, right? So let's start with the traces. Let's look at the xy plane. Of course, this means z equals 0. So it means that we're actually looking at the curve x squared over 4 plus y squared over 9 equals 1. right? And what does that look like? Well, we actually drew it before. That was just an ellipse, sort of elongated along the y. Now you look at it in the, say, yz plane. This means x equals 0. So now your curve would look like y squared over 9 plus z squared equals 1. What kind of shape is that? It's also an ellipse. How does it look?
So 3, 1.
How did it look? Which axis is it stretched along?
Why?
The major axis is along the y, because over here, this is 1 squared, that's 3 squared. So it's stretched 3 along the y, but 1 along the z. And then finally we look in the xz plane. Here we got x squared over 4 plus z squared equals 1, because we're assuming y equals 0. This also gives you an ellipse stretched along the x. This would go from 2, minus 2, 1, minus 1. Okay. So those are the traces in each of the coordinate planes. And now we can sort of put it together.
Nope, not enough.
So this is going to take some visualization. You can sort of see in your mind what wall you're drawing things on. So if we're in the xy plane, where are we? We're on the floor, right? So you want to draw that shape sort of flat on the floor. So the shape was it's stretched along the y by 3, so I know it's going to be stretched. Okay, so now here, I want to hit 3. Trace all the way back. This should be at negative 3. The x, I want to hit 2. Trace along the negative x-axis, that should hit negative 2. Right? And that's our shape. Right? Ellipse, flat on the floor. Right? That's the xy trace. Right? Do the same thing for the other guy. So now we look in the yz plane, and the trace was also an ellipse. Now we're drawing this on that wall. Right? So remember we had the whole corner of the door idea. This was the x-axis, the y-axis, the z-axis. I just drew, well, you'd see a quarter of the ellipse coming along the floor here. It's like on the floor. I literally just draw an ellipse on the floor. Right? Now I want to draw an ellipse on this wall. Right? On the yz plane, it's going to look like this. Ellipse that way. So I know it starts at the 3. On the z, it's going to hit the 1. And if I go down to the negative, it should hit the minus 1. Then I'm going to do the same thing in the xz plane, which means I'm drawing on this wall right now. Right? This wall over here. And that was sort of an ellipse, but it's sort of elongated. This goes to 5. So now it's elongated along the x and it hits the y. So it's at negative 1. It's at 1, 2. And then you sort of put these all together. So you'd realize you sort of draw a capsule. Right? That's your shape. It's called an ellipsoid. Right? It's not a cylinder because you notice that the slices, the circles actually the ellipses actually get smaller as you cut out towards the ends. That's your shape. Right? And we sort of, so it just looks like a capsule, like a, I don't know, magical pill in 3 space. Right? That's the idea. But we figured out how to draw that by just restricting things to 2 variables at a time, right? And drawing the curve that we know how to draw from 2-dimensional space, right? So we figured out that, oh, these are just 3 ellipses that we're putting together. Right? But if you didn't know how to draw ellipses, you're not going to know how to draw this, right? And you need to actually recognize what these shapes are before you can get to the bigger shape. Any questions? Give me another example. Here's a very popular one. Z equals x squared plus y squared. Oh, and by the way, eventually, in the homework, they sometimes ask you to draw the trace, but eventually, like when you're on the final or something, and you have to draw a surface, chances are drawing the surface won't be the question. The question will be to do something else. Integrate over this object, right? And you have to quickly sketch the object, right? By the time you get to that point, I don't expect you to be like drawing traces and putting things together, right? I expect you to go straight to this graph, right? So if I saw the original was x squared over 4 plus y squared over 9 plus z squared, right? Because we're all a 5 in algebra and really know how to draw ellipses, I'm just going to go straight to this guy. And then I'm going to look at that and then I'm going to be like, oh, that's an ellipse in the xy, so I just draw that. So also an ellipse in the xz, so I'll draw that. And it's also an ellipse in the xy, so in the yz, so I'll draw that. And then you sort of put them all together right on the 3-dimensional graph, all at once, right? So basically you're doing this, but you're doing it in each wall on the 3-dimensional graph, right? Instead of just doing it one at a time, that's going to kill a lot of time on an exam. You should just be able to imagine, okay, I'm drawing this picture on that wall, I'm drawing this picture on that wall, I'm drawing this picture on that wall. And the pictures are always going to be things you know how to draw from last semester and before. So that's just a heads up. Like this you shouldn't be doing forever. Sort of like how no one expects you to plot points to draw graphs anymore. Which I noticed someone did on the diagnostic. Right? If I ask you to draw y equals x squared, I don't expect you to plug in 1 and -1, plug into... No, we're beyond that. We're big kids now, okay? So this is the equivalent of plotting points. Drawing traces is the equivalent of plotting points. Eventually I want you to be able to just, oh, I know what that looks like, boom, right? Because that's where we're going. For now, we're moving slow, but we have to, since we're learning, so the next thing is to draw that. Okay, so let's see what these traces look like. If I'm in the xy plane, which means z equals 0, what do I look like? Let me open this file.
It's a point at the origin, isn't it?
It's a point at the origin, because here I have x squared plus y squared equals 0. If any of these were non-zero, I'd get a positive number over there, because they're the sum of squares. Right? The only solution is literally 0, 0 for xy. So that trace is a point. So in the xy plane, it only touches it in one point. What about the yz plane? Which means I think of x equals 0.
Then it's a parabola
Then
on
it's a
the
parabola.
x-axis.
So if the y is here and the z is here, how does that open?
It opens up towards the z-axis.
Positive z, right? That's my trace. Now I'm in the xz plane.
And it's the same thing, opens up on the z-axis.
So it touches a point and it opens in 2 parabolas up towards the z. What does that actually look like in 3 dimensions.
Parabola that's stretched out?
Well, that sounds like you're describing a cylinder. But I sort of get what you're saying. It's sort of hard to describe in words. So, you're ready. One ring to rule them all. Okay. So here, trace, boom. That's it, right? In this wall, I know it's a parabola opening up. In this wall, it's also a parabola opening up. What do I have? What's called a paraboloid. Right? So it's sort of like a cup. Right? Opening up forever.
What would we ever use these shapes for?
Oh, yeah, you do.
Huh?
What's an application of like using some of this?
Once you have the double
Like
integral,
integration?
triple integral,
Yeah.
you use it.
So in general, say you want to find the volume of an awkward shape, right? You figure out how to
Okay.
draw it on 3 dimensions, and you know how to integrate it. Or you're probably interested in physics applications, or if you're doing electric fields and things that are on certain sort of shapes. Right? You have this cylinder, and you want to talk about electric fields. All of the answers are given by integrals, right, in various things. So you want to be able to draw the shape to figure out what's going on, and then set up your integrals on that shape. We're going to eventually integrate over all these surfaces that I'm talking to you about. So, yeah, and this is called a paraboloid. And it's actually a circular paraboloid. Right? And why is it circular? Because if you draw the traces in different things, like if you say z equals 1, right? Then you'd have 1 equals x squared plus y squared. That's actually a circle, right? If on the plane z equals 2, you get a circle again with radius radical 2, and so on and so forth. All our slices here are circles. The radius changes, but there'd still be circles, albeit different circles. Right? Here's a slightly different one. Yes.
What shape was that?
What?
Ellipsoid.
This was
Ellipsoid.
ellipsoid. This was it's called an ellipsoid.
Alright, thanks.
So this one is actually sort of the same. So in the x, y plane, it's just a point again, and then the y, z plane. So this is just x squared plus y squared equals 0. And the y, z plane, you get z is equal to 4y squared. It still looks like a parabola, but it's going to be stretched thinner, right? Here in the x. This is z, this is y, this is x, this is z. It's like a parabola, but it's sort of fatter. And so this guy would sort of stretch this. So it's still a paraboloid, but it's sort of stretched along one axis more than the other. Where each slice here is actually going to be an ellipse. This is called an elliptic paraboloid. So it's sort of like circular, but if you plug in constants here, right, then you divide by that constant and you could get an ellipse, right? So for example, if I plugged in, if I set z equals 4, right, if I want to draw the trace at this point, then I'd have 4 is equal to x squared plus y squared over plus 4y squared. Divide both sides by 4, I would get x squared over 4 plus y squared. That's just an ellipse, right? It's stretched along the x-axis. So that's why I know here I have an ellipse stretched along the x-axis. So traces don't have to be in the coordinate planes. If you're ever not sure about something, you could actually draw it in another plane. What about in the plane z equals 1 or 2 or 5, right? Sometimes you might need that extra information. In fact, I'm going to show you one right now where you would need that extra information, because otherwise it's not going to be clear what they're talking about. Looks pretty harmless. Just put a negative sign. Let's see what happens.
Well, if it's a negative sign in 2D, it's a hyperbole.
Right, you think hyperbola when you see that, right? But what would the guy over there be? Would it be a 0? Would I plug in z equals 0? Turns out z equals 0 is sort of misleading because you actually won't see it. So if you, let's do the traces here.
If it's a hyperbole on a certain axis, it wouldn't even hit z equals 0.
In the xy plane, you have z equals 0, right? And then what would that actually look like? X squared equals y squared, right?
Right.
Which I actually asked you guys to sketch that on one of the diagnostic tests. What does that actually look like?
Actually, that's why it would be a line going out with a slope of
It's
1.
just a line.
It's the absolute value.
That's only you get the positive square root.
Ah, be a big X.
Take square root of both sides, it's plus or minus 1, right? It's actually, you draw the absolute values in both ends. So it looks like that. If we go into y,
Actually.
while you're like, yeah, I know how to draw. Some people gave me absolute value of x. That's half the answer. Of course, he didn't get half credit for that. Let's say yz. What it would look like in yz. Z is equal to minus y squared. Right? If I make that the y and that the z. What if I looked in xz?
Same thing.
Z would be x squared. It's also a parabola. Open up if this is z, that is x. Now it's like, what is that going to look like? Right? So I'm drawing this on these guys. X, Y, Z. So then, okay, over here there's a parabola going like that. Over there there's a parabola going like that. And then there are two lines coming out. Like what the heck, right?
That's correct.
Like what the hell is going on? Right? So it's actually beneficial to do another trace that will give you more information. So that reminded you of something and you told me it was an ellipse, right? So let's say in the plane z equals 1. What does it look like then? Hyperbola looks like this. Right? So now I see if I'm up here at z equals 1, there is actually hyperbolas going at the ends.
Wait, how did you do it that way?
Z equals 1. So I'm thinking I'm hovering above the xy plane
Oh.
at the level of 1.
Okay,
And then I draw that shape.
right.
But then you sort of see that that shape is sort of connecting to the parabolas here. Right? So let's actually figure out what this guy looks like in 3 dimensions. Okay, so we had a parabola going like this. I know there's another parabola it's 90 degrees to this one, rotated, and then going down.
How do you know it's 90 degrees rotated?
Because this parabola is in the YZ plane.
Okay.
So I know it's flat along that wall, while this one is in the XZ plane, so it's flat along that wall.
it's
So
like-
one parabola is along this wall, and the other one is along that wall. Right? So I know there's sort of rotated. So one is going up like that, and then the other one is going down like this. So there's sort of a decrease that way, and then something's falling over this way.
Right.
Sort of looks like a saddle. In fact, that's sort of what it is. If you slice it across z equals 1, you have 2 parabolas going this way. And if I sort of cut it off there, and sort of connect these guys.
Oh yeah.
That's sort of what it looks like. It's like a saddle. If you're on this way, you're going down an incline that way, but then at the sides, it falls off this way. Right? This is where MATLAB comes in handy. You're going to put that equation into MATLAB, and then you're going to be able to turn the surface around and see what it looks like. That's sort of what it is. Those 2 lines, you're not really seeing them because they're sort of under the saddle. Like they're degenerate thing, which goes back into the theory of conic sections, which I don't want to get into, but you're not going to really see them. This is sort of what you'd see. It's like a saddle. In fact, we have a name for it. Saddle. Saddleoid. Yeah, so what do you call a saddle in math? It's a hyperbolic parabola.
I wish we
No, it's
can
not
use this.
hyperbolic. Hyperbolic parabola.
So- Meta is not more complicated.
This is just quick graph.
Yeah,
This is awesome.
we have to try that.
That's what this guy's called, which basically looks like a saddle. There is a list in your textbook. In the first edition, it's page 559. In the second edition, it's page 578. Right, so basically it tells you, it gives you some general formulas. So it might tell you something like, z over a equals x squared over b squared plus minus y squared over c squared. And then that form looks like this shape, right? They give you a general formula and then they give you an example of the shape. And it's just a table with all these guys that you're supposed to know. Yes. Right, so you're supposed to be able to recognize when an equation is describing what to you and be able to draw a random equation that falls from that table. And it's just really summarizing what we've been doing. You'd be able to draw any of those shapes by just drawing the traces, breaking it down in one plane at a time and putting things together. Yeah. It's 584?
Yeah.
So do these extend in every direction forever?
Yeah, this is going up forever and that's going down forever, yeah. And that's it for 10.6. Homework for that is due tomorrow, and I guess maybe tomorrow we can do a MATLAB and draw some of these guys there and see what they look like. So this is why me asking you to draw all those shapes from the past was important. Because they come back. Wait till you see polar coordinates come back. That's going to be fun. There's going to be something called cylindrical coordinates. That's what it's called in 3 dimensions. It really piggybacks off polar coordinates from 2 dimensions. Do you have any questions so far? So that's the general idea of drawing things in 3 dimensions. You sort of isolate 2 variables at a time and draw the shape you know from 2D, and then you sort of put all these shapes together. And if one variable is missing, it just means whatever shape you draw is spread uniformly along that axis. In that case, you have a cylinder. But that's it. Of course, there are many more examples for you to draw in the homework, so you guys can have that. We're moving on to 10.7, where we're going to learn about vector functions.
The exam is including 10.7?
Yes, it's all chapter 10. So in chapter 10, we go up to 10.7.
Okay.
Yeah. So we don't do 10.8 or 9. I think in the book it goes up to 9. But we're only doing up to 7. So this is the last topic for the test. I don't think I'll finish it. I have a lot of notes here. I don't know write all this. Everyone remember what a function is? Like from way back.
It's a machine.
It's a machine. What do you mean?
You put in, and it gives you different output, or output based on an equation.
Another ambiguous way. So if you put in an x, you know what f of x comes out.
Right. It's unambiguous. For example, circles aren't functions, right? Because it fails the vertical line test. But again, in 3D, you don't want to think of things of vertical line test. Because, for example, this could be considered a function of y, even though it fails the vertical line test. Because your universe sort of turns like this. And yeah. Right. But this is not a function because for each x value, you have several y values that are possibilities. So you're not really sure which one you should pick, right? So a function is just something where you plug in a number and it assigns it another number in an unambiguous way, right? Where each output, each input is assigned exactly one output. You call that a function. Okay. A vector function is very similar, except your outputs are vectors instead of numbers. Okay, so let's make that precise. Remind you of some terminology here. what do you call the set of inputs? It's called a domain, right? So if anyone tells you what is the domain of this function, it's just a set of things that you can plug into this function, right? The set of outputs is called? It's called a range. A vector function on R3, that's the three-dimensional space, is a function whose inputs are 3D coordinates and whose output is a vector. Example. I can write down a general. So in R3, of course in R2 the same idea happens, right? It's just two coordinates. You plug in 2D coordinates, or R4 you plug in 4D coordinates, right? The coordinates just go with the dimension, right? So in R3 a vector function could look something like R of t, and this is a curve, is some function of t for the x, some function of t for the y, some function of t for the z. Right? So your input could be a coordinate that gives you a t, and then you can actually plug those guys in. Right? We're going to actually do these in more detail in a bit.
I mean, there in your definition, and I guess if you have a parameterization, it amounts
Right,
to-
it's a parameterization that I'm using.
Okay.
Right, so it means like x is some function of t,
Right.
so that describes the x coordinates, right?
Yeah.
That will give me the first component in my point, right? And then the y is y of t, z is z of t. It's very typical for them to be given you in parametric form, especially when you're talking about a curve, right? For surfaces, you can also write it like this, except you'd have two parameters, right? You'd have two variables in the vector. So here, x of t, y of t, z of t are called functions. What are they? Domain definition. It's sort of like the intersection of the domains of all the functions that appear. to find what works for everybody. Domains. Example, what is the domain of this guy? So this actually gives me a curve in three-dimensional space where the x-coordinate is described by this function, the y-coordinate is described by this function, the z-coordinate is described by that function. Right? So for any value of t, I can actually plot a point in three-dimensional space, right? I can think of it as a position vector. And then the curve is actually the trace of all these points. I'm going to mention it pretty soon. Okay, so what's the domain of that? Yeah?
It can't be less than 2 and it can't be 5.
So for x, what do I need? It can't be 5. It can be anything but 5, because y, 5 we divide by 0, which is blasphemy. Okay. For y, what are the restrictions?
T is greater than 2.
Right. To be evaluated into a log, you have to be strictly greater than 0, right? So on the diagnostic exam, when I asked you, what was ln of -4? It was a trick question. It doesn't exist, right? What's ln of 0? Again, doesn't exist, right? So you have to be bigger than 0 to be able to be evaluated in a log, which means here I need t minus 2 to be strictly greater than 0. So my t has to be strictly greater than 2. I should really be writing x component, z component. For the z component. Any restriction?
T is
T is greater than or equal to 0. Okay, so now I put these guys together, right? Domain of the vector function. So I need to find the intersection of all these domains. I need a set where they can all live together and play happily, right? A nice way to do this, I find, is to actually just draw a number line and start doing those shaded, the things that work. So I know I cannot be 5, right? So where 5 is on my number line, there's a hole, right? So that's for the x. For the y, I know I need to be greater than 2. So where the 2 is, there's a hole. And I know I need to be greater than that, right? So then that would work. For the z, I need to be greater than or equal to 0. So here's 0. I can shade that because I can be equal to 0. And anything above that would work. Now I want to figure out where does everyone work at the same time, right? Well, and this one works everywhere. The first one works at 5 and everywhere else. Right? Going in both directions down to infinity. So where do they all work at the same time?
Greater than 2 and 5.
Of course between here, right? Because all 3 bolded lines are accounted for. On this point, 5 is left out, but then behind that, all 3 are there, right? So I can see here between 2 and 5, open brackets, and then from 5 to infinity. That would be the domain. So TS would be in one of those sets. Between 2 and 5 strictly, or strictly greater than 5, and this function will work. All other parameters are illegal. Because we're still doing real calculus, not complex calculus.
question.
Yes?
Yes, if we were just given the diagram of that and, told to find the limits of the x, y, and z, how would we know which one is x, which one is y, and z?
Oh, you wouldn't. They'd have to like tell you. Which you won't be asking that. That was for the boundary. Let's talk about calculus with vector functions. How do you think we do calculus? Component-wise, right? It sort of everything fits into nicely. In fact, that's a theorem. If your R is equal to then you can actually find dr dt, which you can actually write. The prime notation actually also takes effect here, which is just you differentiate each component. You can also take the integral of r of t, and that's going to be, you take the integral of each component. Plus, you actually get a constant, but your constant here is actually a vector. It's a three-dimensional vector, right? Because you get an arbitrary constant for each component, and you can separate those into a constant vector. And I should have written this before, because limits actually come way before those guys. Those guys are defined in terms of limits. Limit as t approaches a of r of t, you can take the limit component-wise. Limit as t approaches a of x of t limit. So within each component, you just do the calculus like you've been used to, right? You can differentiate each component, or integrate each component, or take the limit of each component, right? So calculus works component-wise here. Just like back in calc A, just a random number. I just said A. The continuity that we understood before, sort of an analogous statement holds here. So R of t is continuous. How do you know something is continuous?
It doesn't have any corners?
No, you can have corners and be continuous.
The limit at each point, or the limit as x approaches each point is equal to the value of the function at the point.
Right. So limit of this is equal to the same as you evaluated it. Whenever that happens, you say you're continuous at the point, and R of t is continuous in general if it is continuous at all points in its domain. All right, so this is continuous at a point, or it can be continuous in general, right? And these are the definitions respectively. Let me do some examples. After these we'll leave and we'll finish up 10.7 tomorrow. So that's a vector function, and we do calculus component-wise. What I'm still wondering is how do you know two vectors are perpendicular?
Product 0.
I know they're parallel.
Cross product is 0.
0? 0 vector. Okay. I find a vector perpendicular to two other vectors.
Cross product.
How do you know if something is perpendicular to a plane? What direction should it have?
This,
It should be
this same direction as the normal
Normal.
vector.
Normal.
I don't know if two lines are parallel.
Scalar
Same.
multiplier is something.
Oh wait,
What's the
vector-
scalar
The
multiplier?
normal
Their direction vectors should be parallel. Anyway, what is this?
Net 0.
Let me
It's a math
call this
problem.
R. In each case, I'll just call it RT. So the limit as t goes to 0 of RT is, what's the first component?
0,
Right? Special trig limit. If you didn't even remember that, you could even do L'Hopital's rule if you remember that. Right? Because it goes to 0 over 0, so you differentiate the top, differentiate the bottom, you take the limit again. 4, because you just plug in 0 because that's continuous. What about that one?
2.
Right. So the limit actually approaches that point, right? So in 3 space, whatever your vector curve is doing, when you get the parameter close to t equals 0, you actually approach the point 0, 4, 2. Right? So that's sort of how you can do it. I mean, that vector curve is really nasty. We're not going to be able to draw that one. We're going to be able to draw some vector curves by hand nicely. What about B? Limit as t goes to 1 of RT in this case is equal to?
It's just 0, 1.
No. A half. Right? Limit as x goes to 0 sine x over x is 1. Right? This I think of as sine of t minus 1 over t minus 1 times a half. Right? This part goes to 1 as the angle in the denominator goes to 0. Okay, so that's a half. This would be 1. That would be? Does not exist. Can't get the log of 0. So overall, the limit here does not exist. Right? If one component messes up, everyone gets messed up. Right? So these two are defined there, but the third component, where's the z? I don't know where he went. Got drunk, wandered off somewhere. Can't get the party together. Right? So does not exist. Right? So all components have to play well together. Right? One was just a really bad point. Right? It wasn't in the domain, and the limits doesn't exist. Right? And even if I did the one-sided limit, where you can get like infinity, infinity can't be a component to a vector. So in either case, it won't exist. Can we differentiate it though? So r prime of t equals how do you differentiate that?
Negative 1 over 2
1
minus
over
5.
t minus
I was seeing if someone's going to say ln. Okay, how do you differentiate ln of
1
t?
over t minus
How do you differentiate this one?
1 over 2 squared t.
D, I define integral of RT. Integral? You guys are afraid to say ln now? I have no problems with ln in general, I just have problems with the misuse of ln. Right, so that's ln. You're like, oh, he's going to hit me if I say ln. No. What's the integral of the middle one? bare your soul.
Fine,
What?
whatever that
That's so long.
Just say, you're right.
T minus 2 ln.
What's the integral of ln x?
X ln x minus x.
Right, here your x is just t minus 2, right? You can do a substitution, du would be dx. So this is just x ln x minus x.
Plus,
Integral of that one. The plus c we do at the end, right? We just put a plus
right,
c.
Again.
yeah.
It will be a vector at the end. Right. So in here I could put a c1 and a c2 and a c3, but then you can extract those as a vector with components c1, c2, c3. So we can put the constant at the end. Right.
One
So what's the
over-
last one?
1 over 2 root 2, root t.
2 over 3
2/3.
t 3 over 2.
Plus t.
Close that, and then you put a plus, ran out of space, c. Right? Where notice that c is actually the components of c1, c2, c3, where each of these are the constants of integration for each constant. That's it. We'll pick up tomorrow. And maybe we'll do some MATLAB to supplement 10.7. You want to play tomorrow? We can do one on Thursday since we're not doing a test.